Hi everyone. Today we are going to be continuing our series on optimization. So if you guys didn't watch part 1, here's basically a quick recap of what optimization is. So imagine you have some arbitrary function f of x, and f of x looks something like this, alright? So you notice these two special points right here where the function sort of maxes out and minimizes out. It starts increasing and then all of a sudden it just starts to decrease, but then for this point it decreases and then goes back up. So the goal of optimization is to find the location of these 2 points right here. And the way we do this in calculus is we acknowledge the fact that when the function goes from increasing to decreasing, or decreasing to increasing, when the function changes directions like that, the tangent line at that point is horizontal. In other words, the slope of the tangent line is 0. And the way we notate this in calculus is f prime of x is equal to 0. Optimization basically contextualizes this idea and puts it into arbitrary scenarios. In the last one, we took a look at fencing and building a backyard. And in this one, we're just going to look at 2 arbitrary numbers. So let's go ahead and apply this concept to this scenario right here. So the question says, find 2 numbers whose difference is 16 this should say and whose product is as small as possible. So what this is telling us is that we need to find some sort of minimum, and we have this constraint right here to make this possible. So here's the idea. So 2 numbers, let's call this x and y. So x minus y is equal to 16, and we'll just assume that x is greater than y. So that way we don't have to do any finicky absolute value stuff. We don't have to worry about any of that. So here's what we'll do. We know that x minus y is 16, and the product of these 2 numbers can be written as p equals x times y. This is our product of the 2 numbers. So here's what we know. We know x minus y is 16, so we can say that x is equal to, let me write this in a better place. So we know that if we take this constraint here and solve for one of the variables, x or y, let's do x in this case. We know that x is equal to y plus 16, and we get that just by moving this y to the other side. So what we have here is we have an expression for a certain variable, and what this allows us to do is we can substitute this expression into the respective variable here for this equation right here. So here's what we're going to do. We're going to take this expression and substitute it in for x. So we get that p is equal to y plus 16 times y. And then we'll go ahead and just distribute out this y. So we get that this is y squared plus 16y. Now here's what we're going to do. We have this expression for p. So basically what it's saying is like we have p as a function of y almost. So if we were to take a look at the graph of this, it would look something like here. It would look something like that. Obviously this is a terrible looking drawing, but it doesn't matter. So yeah, we have this expression, this function for p as a function of y. So we see that we have a minimum at this point right here. We don't know what this point is. So this right here would be our y value. So our goal here is to find this minimum point. And again, the way we do that is we notice that at this minimum point right here, the tangent line is horizontal, or the slope of the tangent line, or for IB students, gradient of the tangent is 0. So what we can do is we can take the derivative of p, set that equal to 0, and we'll get our y value. So let's do it. So we get that dp over dy, or you could just say y, or p prime, that works too, is equal to, if you take the derivative of this expression, we get that this is 2y plus the derivative of 16y is just 16, and this has to equal 0. Now all we have to do is just solve for y in this equation. Sorry. So we get that this is equal to 2y is equal to negative 16, divide both sides by 2, we get that y is negative 8. So this is the first of the two numbers that we need to find. Not only do we need to find what y is, we need to also know what x is. Thankfully, we have an equation here that we can use to find x. So now that x minus y is 16, so let's plug in negative 8 for y. When we do that, we get x minus negative 8 is equal to 16. These two minuses cancel out, so we get x plus 8 equals 16, and then x equals 8. Now this should make sense, right? This should make sense, because if you multiply any other numbers with this constraint, you'll get that the product will not be as small as the product you would ascertain from this. So the product you would get from this would be negative 8 times 8, which is equal to negative 64. This is actually the smallest possible product you can get. And you can check this with any numbers. Like, let's say you have negative 7 and 9. That's going to give you negative 63, which isn't as small as, which isn't as negative as negative 64. And then 6 and 10, right? That's going to give you negative 60. And so on and so forth. You'll notice that this number gets closer and closer to 0 and further away from the minimum. So that's pretty cool about optimization. Optimization basically gives you a way to find the answer to these sort of abstract problems. And these can be applied contextually. Not only could they be applied in a fencing scenario, like in part 1, but they can be applied in future scenarios. And that's where we'll pick up next time with this series. I hope to see you then.